Here is the third isomorphism theorem. Let G be a group and H K two normal subgroups of G where H contains K. Then K is normal in H, and we can define a map of G mod K onto G mod H by associating with each coset xk the coset xh. It is immediately verified that this map is a homomorphism and that its kernel consists of all cosets xk such that x is in H. Thus we have a canonical isomorphism bracket G mod K mod bracket H mod K to G mod H. First of all, I have the setup. Let G be a group and HK2 normal subgroups of G where H contains K. Then the first claim is that then K is normal in H. Since K is normal in G, for all G in G and K in K, G inverse is in K. And H is a normal subgroup in G, which implies all H in H is also in G. Then for all H in H and K in K, HK H inverse is in K. Thus, K is normal in H. The next claim is that we can define a map of G mod K onto G mod H by associating with each coset xk the coset xh. First, I would like to check whether this map side of G mod K to G mod H where side of xk equals xh is well defined. Let xk equals x prime k in G mod K, then x inverse x prime k equals k. Since x inverse x prime is in K and H contains K, x inverse x prime is also in H, therefore xh equals x prime h. This implies that psi of xk equals xh equals x prime h equals psi of x prime k, and hence the map is well defined. To verify that the map is surjective, since any coset xh in G mod H, x is in G and xk is in G mod K. By the definition, psi of xk equals xh. This means that every coset in G mod H has a pre-image. Thus, the map is surjective. The following we have, it is immediately verified that this map is a homomorphism. Since side of bracket xk bracket x prime k equals side of x prime k equals x prime h equals bracket xh bracket x prime h, and side of k equals side of ek equals eh equals h, this map is a homomorphism. The fourth claim is that its kernel consists of all cosets xk such that x is in H. By the definition of kernel, kernel of psi equals to a set with all elements xk in G mod K where side of xk equals h. Since side of xk equals xh equals h, x must be in H. Hence, kernel of psi consists of all cosets xk such that x is in H. Finally, thus we have a canonical isomorphism bracket G mod K mod bracket H mod K to G mod H. By definition, H mod K equals the set with all coset xk in H where x in H equals kernel of psi. Then, bracket G mod K mod kernel of psi equals the set of all cosets bracket gk kernel of psi in G mod K where gk in G mod K. Since bracket gk kernel of psi equals bracket gk bracket hk equals bracket gk bracket kh equals gkh, and h contains k, bracket gk kernel of psi equals gh. Thus, there is naturally an isomorphism bracket G mod K mod bracket H mod K to G mod H. And this is what people usually call the third isomorphism theorem.